Hi, my name is Reddy Chagam. I'm the cloud architect from Intel Corporation. This session, I'm going to talk about Mortimer, a high-performance scale-out storage stack that uses the persistent memory and NVMe SSDs. I will start with Mortimer overview, and then I will cover details behind the motivation on why we are doing Mortimer, and then switch over to the architecture, cover the architecture, high-level architecture, and then uh, talk about the metadata, the core data structures that are actually used in a Mortimer, and then if time permits, I will do the demo, and then jump onto the summary and next steps and wrap up the session. Mortimer overview. So Mortimer is essentially a distributed storage stack that uses NVMe or Fabrics protocol, both for the client connectivity as well as the cluster connectivity, and it uses the Optane persistent memory and SSD as a way to do the fast metadata lookups and optionally write buffering to speed up the read and write data path IO. Um, the key difference compared to what you see normally with NVMe or Fabrics based implementations is Mortimer uses this for both client data plane activity as well as the cluster replication data plane operations. So it's an end-to-end NVMe over Fabrics based protocol to build a distributed storage stack. Um, Optane persistent memory is the primary focus for this talk. And Mortimer uses the app direct, highly optimized data structures in app direct mode to get to the low latency and high performance. Optionally, we can use Optane SSD as well, but that's not really the focus of this talk. And then we can also do fast write buffering with either one of the media types. Um, as with any high performance storage, the implementation essentially uses the lockless and pole mode, primarily to ensure that it's a highly efficient, from a compute perspective. Uh, Majority of the distributed storage stacks out there use thin volume provisioning, so we have to do the similar implementation in Mortimer. So when I say thin volume provisioning, what it means is when you create a volume, let's say 2 terabyte volume, it's not really consuming any capacity in the storage cluster. As and when you write into the volume, the space is actually consumed. That's what is thin volume provisioning. Um, the data is actually replicated based on the policy. It could be no replication or it could be two-way replication. So the replication flows are supported as well. And then if there is a failure on the storage node, obviously we need to be able to recover the data from the storage node, from a failed storage node by reinitiating the replication from the surviving storage node onto the other node in a cluster. So the rebalancing and recovery is an integral component for the distributed storage cluster, which needs to be implemented in Mortimer as well. Authentication and authorization, essentially they need to be able to authenticate and authorize to secure the interaction to the Mortimer backend from the client flows. So we have to implement that. And then the backend to the NVMe SSDs doesn't use the file system primarily because of the overhead associated with the file system. So I will cover a few data structures that are being used to ensure that we can actually do raw block access to the NVMe SSDs by using the metadata data structures that are actually sitting in the Optane persistent memory. Now, what's the motivation behind Mortimer? If you look at the emerging workloads like machine learning, deep learning, 5G, edge, they're all driving the need for high performance, which is essentially driving the need for all flash storage implementations. But of course, all of them require some sort of a data protection as well. If there is one target type of implementation, if it fails, you get into data loss situations. So there is a need for distributed data storage with a very high performance and low latency type of requirement. NVMe over Fabrics protocol being a dominant one that is gaining traction in the industry, why can't we actually take advantage of NVMe over Fabrics protocol and adapt it for distributed storage software as well? Persistent memory has been there for the last few years, couple of years or so. The question is, well, how can we take advantage of the persistent memory with the load store semantics to achieve the low latency? And then platform offloads, and then emerging technologies like compute express link can also be exploited to deliver a low latency distributed storage performance. Having a lightweight data path coupled with the standard protocol like NVMe or Fabric semantics really helps for emerging trends as well. So for example, computational offloads. You can really take advantage of the computational offload type of capability that gets delivered on NVMe or NVMe or Fabrics based block protocol. The other aspect is if you have a common NVMe or Fabrics based distributed backend, it can help in plugging in with the existing scale out storage services, things like Kafka, database, big data type of database services can really take advantage of a distributed backend that provides the resiliency properties as well, plus the high performance attributes. So the Mortimer design philosophy is we need to be able to take advantage of the NVMe or Fabrics protocol traction in the industry, extend that with the distributed storage semantics, and take advantage of the persistent memory, app direct with load store type of programming model to really deliver the low latency that open source communities are looking for. Now let's take a look at the architecture. So the top side is essentially the NVMe or Fabrics client. So the goal of Mortimer is if you have a client today that uses the NVMe or Fabrics based access through kernel drivers, we should be able to take advantage of that without actually changing the kernel side, the runtime driver, code. So that's one way of integrating with the Mortimer backend. If you have a SmartNIC type of capability, obviously you have a bit more freedom to add rich data services, things like you can do the compression. You can actually have encryption type of data services on the client. And of course, you can actually implement that in the user mode. So it essentially gives you a bit more optimized way of deploying the client runtime through SmartNIC compute capability. That's the other way of instantiating and connecting to the Mortimer storage backend. Now, typically, most of the distributed storage stacks, when you say you are creating a volume in a cluster, normally the volume is actually sharded across a pool of storage nodes. We do not have that type of capability and the standardization in the NVMe or Fabrics. If you do want that type of capability, you will end up using the kernel driver that is optimized for sharding a volume across pool of nodes. It will continue to use the NVMe or Fabrics protocol, but there is a notion of dynamic binding when you want to do shard, and that dynamic binding is actually decided at runtime based on the volume and the shard. It may be located anywhere in the cluster based on some sort of a consistent hashing scheme. And it has to connect to the cluster service to map to the storage cluster to really understand the endpoint for a given slice of the volume that need to be actually distributed in the cluster. So that requires a custom kernel driver. The cluster service essentially uses the consensus protocol, and our current thinking is we will use the Raft open source implementation out there as a way to integrate the cluster service to monitor the cluster, trigger the recovery and rebalancing when there are storage node failures that are not recoverable. Storage backend, the front end is messaging layer. Messaging layer supports both NVMe or Fabrics protocol for the client connectivity as well as the inter cluster traffic. And then we use the RPC for the management traffic to essentially do the monitoring, collect the performance data, and connect to the cluster service, and bring up the nodes, add the nodes, and all the maintenance operations. Storage service is really the critical backbone for Mortimer. Storage service uses the the metadata and the optionally write buffering with Optane persistent memory and Optane SSD. And then where it makes sense, it uses DRAM as a way to speed up the lookups. And then the backend for NVMe SSDs uses the poll mode techniques as a way to do reads and writes in and out of the drives. Now, there is a possibility that we may look at DRAM-based metadata. There are certain platforms out there that are actually that have the capability to provide battery-backed, and we are looking at ways to support that kind of configuration where there is a platform that has the battery-backed DRAM capability. We could potentially use that configuration as a way to store the metadata. So the libraries are actually tuned to ensure that we can actually support DRAM-backed metadata that gets persisted through the platform design or through the Optane persistent memory through load store semantics. Let's take a look at the storage backend. The messaging layer at the top is extensible enough to expand it beyond the block, NVMe or fabrics-based protocol. So, for example, you can actually extend, and support Ceph, Rados type of block-based protocol. You can also extend using, S3-based protocol as well, even though the intent for the initial release will not have these capabilities. The I/O that is actually coming in goes through the object layer. The reason we have an object layer in Mortimer storage backend is whenever you have a volume, if you were to actually host the entire volume content from one drive, you will potentially end up getting into hotspots, especially when you have a volume that is very demanding from a performance and throughput perspective, that where other volumes are coexisting on the same SSD drive, you may actually see hotspots. Now, for us to actually smooth the hotspot behavior within the storage nodes, need to be able to actually take up the volume, slice into objects, and distribute them among all the NVMe SSD drives inside a storage node. Now, for that, we need to actually convert that into objects and then distribute them. That's really the purpose of the object layer. Metadata management, as I mentioned in the previous slides, essentially uses the Optane persistent memory and in future Optane SSD as a way to store the metadata. The metadata could be when you have an object, you need to be able to actually look at where is the object located, what are the NVMe SSDs that are hosting this object, and exactly on that SSD, which LBAs are actually being mapped to read and write data from. So all that content is actually part of the metadata management. And then the write buffering goes through the journaling, and we can loosely call that as write buffer as well. And then the flusher is the background job that routinely wakes up, reads the write buffers, and then flushes to the NVMe subsystem. Optionally, we can have cache. Cache is essentially meant for if you have an Optane SSD and if you have if you are using the metadata with Optane SSD, certain data structures we may want to cache them in memory. So that's one purpose. And there are certain objects that we may, that we may want to cache through DRAM. We can do that as well. NVMe subsystem uses the poll mode driver that actually comes from SPDK, block IO driver. Essentially, it reduces the compute tax by using the poll mode and lockless design pattern that gives us the scale plus low latency plus reduced compute tax on the storage node. The design is such a way that we can actually take advantage of the platform offloads. So for example, if you have custom firmware extensions in the NVMe SSD, let's say through if there is a custom firmware that actually gives us ability to get list of LBA sectors that are actually corrupted, you can do that because the drive does the background scrubbing, and if there are unrecoverable sectors, it can log those sectors. Mortimer can actually tap into that data and then look at all the objects that are associated with those LBAs, and then proactively uh, fetch those objects from the other nodes in a cluster and patch them, as opposed to using the brute force read the entire content of SSD drive to figure out exactly which ones are corrupted. Those types of offloads are very important, primarily from the platform perspective, where we can actually reduce the compute burden, and we can also use the compute that is available to service the client and cluster data plane traffic. If a platform has encryption and compression type of offloads, we should be able to take advantage of that as well. So the design theme is we need to be able to not only take advantage of the NVMe or fabrics-based protocol for the client connectivity and the distribution, data distribution within a cluster, we need to be able to take advantage of all the offloads that are available in a platform, either from the drive firmware type of capabilities, as well as the silicon SoC capabilities. In a two-socket type of configuration model, you end up actually having one Mortimer daemon per socket managing all the storage that is actually available on that socket. So in essence, you are essentially looking at two storage daemons in a two-socket type of configuration. The writes that actually go through the journaling and flushing, normally for streaming type of writes, as you can see, there is a short circuit path which essentially looks at the large objects. And if these large objects are actually new objects, there is no need to actually buffer them and then read them right into the NVMe SSD, because it will significantly reduce the bandwidth in a given platform. So the goal is to look at intelligently the optimizations needed where we don't have to do the buffering brute force way, but look at only certain operations that absolutely require buffering and do the buffering. Let's take a look at the message processing pipeline. Now, I talked about pole mode lockless constructs. If you look at the client traffic that flows in and out of the storage node, in the front end of the pipeline, you have the network activity that gets processed through set of cores, and then gets actually transferred to the set of cores that actually look at the message type by doing the decoding, decrypt, decode, authenticating the user, making sure that the message is actually coming from an authenticated user. And then once the message is decoded and based on the type of message, it essentially ships to the right set of cores that can actually process. So for example, if it is a data plane type of traffic, once the message is decoded, that actually gets published to the queue to a given NVMe SSD that is actually supposed to process that data, plus obtain persistent memory that is supposed to do the lookups. Or if it is reads, it may be actually sitting in DRAM. So the goal of the message decoding and routing and the message router is to look at the type of messages and distribute it to the right cores that are actually responsible for processing those messages. Now, there are two types of messages at a broad level. One, there are either stateful, processing, type of tasks, or there could be stateless. So the stateful will be something like when you have to do the drive IO, you don't want the drive IO to be submission completion queues. You don't want them to be actually floating around among all the cores. You want to be able to run them on a specific set of cores. You want to be able to do pole mode on those cores, and then not getting into pervasive locking implementation. So those are actually the stateful tasks that actually run on specific set of cores for its lifetime. Now, the stateless tasks, things like if I want to do the message decoding, I absolutely don't need to run it on a specific core. I can run it on any pool of cores. So the stateless tasks execute on a pool of cores. And basic primitive implementation for the initial release will be just do the round robin, lightweight, core scheduling. You have the pool of cores, and you essentially do the simple, random or round robin based scheduling to be able to actually run those operations on the stateless pool. Now, you can actually, our current thinking is that um, NVMe SSD, ideally, we want to be able to have one core drive one NVMe SSD, completely. But it's possible that as you actually get into more and more higher performing PCIe Gen 4 and Gen 5 type of, capable NVMe SSDs with higher performance, one core may not be able to sustain, from a throughput perspective. So the design will essentially blend itself into partitioning the NVMe SSD, and you can actually run them on multiple cores as well. Now let's take a look at the persistent memory data structures, just to give you an idea of how these data structures are actually optimized to reduce the data path IO. In the previous couple of slides, I talked about all the IO, block IO coming in and out of the storage node gets actually operated at an object level. Currently, in the current implementation, object metadata is actually stored in the cuckoo hash table. So when you actually look at the hash table, I'm not going to go into the details of the cuckoo hash table algorithm, but at a high level, an object, you compute a hash. There are two hashes, and currently the implementation uses murmur hash. So it computes two hashes for a given object, and then actually tries to map that object into two distinct rows. If the first row where it gets mapped into is filled up, it goes into the second row and looks at all the slots and see if it's filled up as well. When everything is filled up on both rows, it will pick one of the random entries in the first row and evict that. And that object essentially goes through the same process of mapping, computing hashes, two hashes, and mapping into the object table. And that process iteratively, will find an empty slot in the object table. On an average, this essentially gives O1 type of, the complexity and the overhead. Extremely fast from lookups perspective. However, it is not that flexible. So let's say, for example, if an object table is not big enough, you'll have to go through the maintenance activity. You need to shut down the storage node and you have to go through the maintenance activity. So object table sizing has to be perfect to avoid any maintenance, type of activity on the storage node. Now there are alternate design options too. We can take an object table with the cuckoo hash table type of implementation, and then we can create an overflow, the tree type of a data structure, B tree type of a data structure as an overflow table. But all those things will add bit of an additional lookup if there is essentially miss from the object table. It has to go to the B tree and do the lookups. But in general, that's an option. So every object includes few critical attributes to essentially locate an object, inside the drive, NVMe SSD drive, and then also look at all the outstanding and pending operations that are actually going on for a given object at any given time. And those operations may be staged in the write buffer, which is on the right-hand side. The object metadata could be, E tag, which is essentially, a hash of an object. So in case when you read an object from the drive, you can compute the hash and then, look at if the object is corrupted or not. Who is the owner? When was it created? When was it modified? When was it updated? All kinds of, few interesting metrics you can actually keep track of. Attributes. the reason we created an extent map for an attribute is essentially if you have an object that has large number of attributes, it's not practical for us to keep that in the expensive persistent memory type of media. Um, we would rather actually keep that on the NVMe SSD itself. So attribute extent map provides that extension capability where you have large number of attributes, then you essentially map it to the drive through the extent map. And then obviously the data will be mapped to the drive as well through the extent map. All the pending operations for a given object get actually tracked in the op queue. Um, and these opq buffers may point to, especially for inserts and deletes, the write activity may actually be tracked. If they're buffered in the right buffer, it needs to actually point to the right buffer. And of course, this write buffer is persistent, whether it is platform-based, DRAM, battery-backed type of write buffer, or persistent memory-based. It need to be, it need to be staged, and then, behind the scenes, it gets flushed, right? That's really the reasoning behind on how the object tracker essentially includes all the metadata to tie into the right buffer as well as NVMe SSD. Now, every drive has certain amount of metadata that that is actually stored in the persistent memory as well as inside the drive. So persistent memory metadata for a given drive will point to what drive type it is and what is the namespace ID and maybe a partition of the drive and including security credentials and everything else to unlock the drive. All those pieces of information is stored in the persistent memory data metadata for a given drive. And then drive may have metadata that essentially points to where is the metadata stored in the persistent memory partition. So it's almost like a reverse lookup back to the persistent memory metadata, right? So it essentially is a bidirectional, mapping between persistent memory and the NVMe SSD. Now, for us to actually do the write into the NVMe SSD, we have to go figure out which ones are actually available that are not used up, which sectors or blocks inside the drive are available for new writes, or even for updates that extend beyond the existing allocated range. We use a very simple high performance lookup table based on power of 2 binning, which is on the left hand side. Essentially, you have a bin as the lookup. So every bin essentially indicates the number of, let's say, for example, you have bin 8. This bin includes at least 8 contiguous sectors that are free, all the way down to the next bin, which is 5. So essentially 8 to 5 contiguous bins to 8 contiguous bins is actually stored in the bin number 8. Now, the binning part and storing is aligned with essentially a page. So every page includes starting block number and number of blocks that are actually available for allocation. And then there is a attribute called use slots as a way to track how many slots are actually used, how many slots are empty. And then it's a linked list for every bin. You may have X number of free pages, X number of pages that are actually linked together in case it goes beyond one page worth of free slots available. Now, typically when you start up in the beginning of the drive provisioning, it essentially takes up the highest bin and then start from there onwards. As it starts actually getting consumed, the number of the slots will essentially get split into the lower bins and slowly graduating to the lower bins as they start consuming more and more LBAs, and number of free contiguous blocks go down. But the intent here is that we use the persistent memory to allocate X number of pages during the bootstrapping time, when it actually does the PMEM metadata partition formatting, it grabs X number of free pages based on the drive size and all that stuff. And then um, it will avoid the dynamic allocation of memory by just taking those free pages and then start using them. Bunch of them could be used for allocated, free block entries that get mapped to different bins. Bunch of them could be available for allocation. Bunch of pages could be be readily available in the free pool that can be used to allocate to any one of those bins. So this avoids memory allocation at runtime. That's one part. The second thing is using a sizable, 4K type of page aligned chunks. It creates a sequential I/O type of behavior, especially for persistent memory, and cache affinity and locality. So it speeds up the lookups when you are actually looking at lots of I/O requests coming in from the same bin. You don't have to actually go randomly pick each one of them from different areas in the persistent memory. So there is a sequential pattern, allocating all these, grabbing all these pages and managing the allocation of those pages at runtime avoids the memory allocation, which significantly reduces the overhead associated with dynamic memory allocation and improves the performance. Now let's take a look at the write buffering. So typically when you do the write buffering, the simplistic implementation will be, I can have a write buffer, and whenever I want to write something into the write buffer, I take a lock, and then whenever I want to actually read from a write buffer, I take a lock and then flush it. Now the problem is when you actually do the locking on, for writing IO or reading from the write buffer, it essentially serializes all the, at least majority of the operations. And it's not persistent memory friendly, primarily because you need to be able to, allocate the write buffers that are 4K aligned at runtime, and I need to be actually take those write buffers and do a DMA directly to NVMe SSDs. So we have to tailor, make the data structure such a way that we reduce the locking significantly or even avoid locking completely, where writes to the persistent buffer can happen in parallel, whereas the flushes can actually happen in the background without taking any locks. And then we can actually do effective DMA to the drive without actually allocating, another set of buffers just to do the IO to the NVMe SSD. So Mortimer uses a concept called, it takes a flat persistent memory region, a sizable chunk. Let's assume it is few megabytes. It takes first X number of bytes and uses that as a header. The reason why we split the header into separate compared to the DMA buffer is obviously the DMA buffer is meant to be used for writing to the drive directly. So we don't want to mix headers and buffers in the same region. So it slices the header into the separate region and the DMA buffer into the another region. Now, the DMA buffer is actually sliced into one more granularity, which is called chunks. Now, the chunks are independent entities when it comes to doing IO operations. So you may have chunks at any given time in one of the, there are three different types of queues. So you have a queue that where you are writing active IO to the chunk, or you have the chunks that are actually in the flush queue, where you are actually flushing the IO to the drive, or the chunks are available for allocation in the free queue list. The chunks actually are connected together through the linked list, and essentially go through the at any given time it can be sitting in one of those queues, and having IO operations that are going through when an IO is going through a specific chunk. in a WIP queue, it is not ready for flushing. Only when that chunk is actually filled up, it essentially goes to the flush queue. Um, Only when the flush queue computes all the flush operations, it actually won't, only then it will go into the free queue. So WIP operations and flush operations actually happen in parallel without taking any logs. Now, every chunk in the header essentially gives some information about how many objects it has, how many buffers are used. Anytime you want to actually change any of this, you are essentially changing just the header and then persisting that in the PMEM region. So your persistence and commits and everything becomes extremely fast because you're operating on a very small set of uh, bytes, and becomes extremely fast from a metadata manipulation, persistence, and commits to the persistent region. Um, each one of those log chunks actually point to all the outstanding operations that actually point to object metadata, and then it also points to the buffer that holds the data for a given operation, pointing to the specific chunk. Um, this design blends very well, where you can actually look at centralizing the right buffer. Let's say you have one or two dedicated write buffers coming from, let's say, Optin SSD. You can actually centralize the write buffers that are actually flowing in and out of the storage node, and then actually have flush queues for a given drive, um, operated from the cores that are actually dedicated for that drive IO operations. So this architecture kind of helps you in both ways, where you get the lockless um, poll mode type of pattern without taking any logs. And then you have a design on the logging and chunking where you're operating on a very small data set to change the state to whether chunk is used or not, how many objects are actually part of a chunk. And then when the number of objects actually go down to zero, you are essentially changing the number of objects to, changing just that specific field, persisting that in the persistent memory, and then pushing it to the free queue. So the intent of this design is essentially to make sure that we are operating on a very small data footprint when it comes to manipulating the data and persisting the data on the persistent memory, right? And getting the performance needed without taking any logs. That's really the crux of the uh, write buffer design. Now, let's take a look at how these pieces actually work together through the demo. Um, in this demo, I will show you a target and initiator that are actually flowing through the Mortimer layers. It's a very simple demo. Again, it uses the persistent memory NVMe SSD. When you look at the configuration, the sample configuration for this demo is, if you look at the sample configuration, we are essentially using two persistent memory partitions. In fact, on this node, there are 4 partitions. These are all FSDAX based mounted partitions. It is using 2 partitions. Each partition holds just the metadata. In this configuration, we are only doing the metadata, not the write buffering. And then the durable data is actually stored in the NVMe SSD, which is actually configured for each one of those partitions as a pair. These are actually Intel P4610 drives. So let's start the storage service. This is starting the Mortimer storage service. Mortimer uses essentially 3 development kits: data plane development kit for high speed, ring and mem table, lookups. It uses the persistent memory development lib PMEM layer for the persistent memory, and then it uses the SPDK for both NVMe or Fabrics instantiation as well as the block IO to the NVMe SSDs. Now, on the right-hand side is the initiator. Let's take a look at how many objects that Mortimer is exposing. So here on the right-hand side, I'm just using the NVMe or Fabrics, nothing else. So it's discovering all the volumes. For this demo, it created 2 volumes. So you can actually see there are 2 different volumes. And I can actually run a sample performance benchmark. This is the user mode SPDK perf example app. It makes easy to just run the performance. Now it's actually running the 4K random write on this volume. Now, as you can see, the progress here, it's around 270K IOPS or so, coming from 1 volume. Now, this whole IO path, all the way from the right-hand side initiator to the left-hand side target, is actually flowing through NVMe or Fabrics client to the storage target. On the storage target, it is actually traversing through the object layer, the metadata layer on the persistent memory before it can actually map the write IOs to the NVMe SSD. So that entire data path IO is what you can actually see in this demo. It doesn't have the replication flows yet. The plan is to actually implement the replication flows and then actually get ready for scale testing and publish to the open source community. As you can see here, it ran for 30 seconds or so. In the interest of time, I just ran it for 30 seconds. The number of IOPS for this volume is 273K. These are the write IOPS. And the latency, average latency this is the NVMe media. So you expect the latency, and this latency includes the media plus persistent memory latency, which is around 200 plus microseconds or so, right? So hopefully you got an idea of how Mortimer is implemented with the persistent memory data structures and how they are actually optimized to reduce the metadata changes during a typical IO flow from the client to the storage node cluster. So just to, in summary, Mortimer uses the NVMeoF fabrics with some extensions to get to the distributed storage semantics. I briefly talked about connecting to the storage node requires NVMe client side changes. If you really want to shard it across the cluster with the dynamic binding to the the storage node for any shard in a volume, you need a custom driver. So there are certain extensions needed, but you can use the existing NVMe or Fabrics plumbing from the client side to be able to do most of the operations in a very primitive way, but it essentially addresses most of the current flows. We use the persistent memory as a way to store the metadata. Plan to extend this with Optane SSD as well. Persistent memory usage for the metadata is a very, very critical component to reduce the latency for metadata lookups, and uses the persistent memory with a combination of highly optimized app direct data structures. I briefly talked about optimizing the data structures by splitting the headers and by changing only the absolute needed portion of the header and committing that to the persistent memory, as opposed to taking a very brute force data structure type of implementations that we normally do with DRAM based programming model. So we have to actually pay attention to persistent memory data structures very, very closely. Otherwise, the performance will dramatically go down if you don't optimize it and do it, do the design from ground up with persistent memory in mind. Poll mode in lockless design is used across the board, both for the client operations, cluster operations, as well as the drive operations. That's an integral part of the design to ensure that we are actually reducing the amount of compute tax on the storage node and get the low latency performance needed for exploiting the all-flash type of configurations. We plan to open source this sometime in the first half of next year. Need to get the replication flows working under volume, under scale, with all the consistency type of attributes that are actually tested thoroughly, so that the community can actually start contributing. I kind of briefly alluded a few times about NVMe or Fabrics protocol being a very dominant protocol that's standards based. But at the same time, we need to look at this protocol from the perspective of distributed storage and what other constructs that are actually needed. Location transparency, dynamic binding is one of the key things that are needed on the client side. The replication aspects between the storage nodes, the transaction semantics, all those consistency semantics are actually needed to essentially make sure that we can use the NVMe or Fabrics for the distributed storage protocols as well. So this requires a little bit more groundwork before we can actually put it in front of the SNIA community and figure out the best way to evolve this NVMe over Fabrics protocol for scale out storage. That is absolutely needed for us to actually make traction and to address the industry-wide pain point for all flash type of storage configurations, where you really need an extremely performant, high performant protocol that is lightweight, standards based, easily integratable, but at the same time it gives you all the benefits of the the low latency and all that stuff that is needed for flash based systems. With that, thank you for your time. Send us comments on if there are send us feedback on what data structures make sense. If you have feedback on the design itself, do feel free to reach out to us. Would love to hear your feedback on Mortimer design, and we look forward to your contributions starting the first half of next year. Thank you.